A quick reminder that there are two kinds of kinetic energy. Anytime you want to make something move, whether it is in a line or make it rotate, you need to give it some energy to make that happen. And then once it's moving, it'll have that energy inside of it. So translational kinetic energy is the same as linear kinetic energy. It's the kind of kinetic energy we've been talking about for a long time. Linear kinetic energy would be, for example, if I've got this wheel here and I just want it to move in a straight line, I would have to do some work on it. And if it's moving in a straight line like this, it would have kinetic energy equal to 1/2 mv squared. Rotational kinetic energy, on the other hand, is the kind of energy, is a different kind of kinetic energy, but it's still the idea if I want to get this to spin, all of the parts are moving. And so I still have to give it kinetic energy, but we talk about rotational kinetic energy when we're talking about something that is rotating around an axis. And then if we have a solid object like this that is rolling along the ground, so it is both moving forward, which requires linear kinetic energy, and rotating, which requires rotational kinetic energy, so something like this, where I've got my wheel rolling along a surface, it has to have both linear and rotational kinetic energy, or both translational and rotational kinetic energy. So we want to try to figure out an equation for our rotational kinetic energy for k rot. So let's talk about how to do that. So we're going to start off with the simplest possible situation. Imagine we have a point mass that is rotating around an axis. And unlike the wheel, all of the mass exists at a single point. And so here is the path that it is rotating around. And we've got our radius out to the point our mass is at right now. And let's imagine this one is going, let's make it go clockwise. So we have our mass of mass m. And if we want this to rotate around our thing here, around our circle here, we could, as long as it's going at a constant speed, we could just imagine that this is in uniform circular motion. So because all of the mass exists at our point, we can just say that, well, at any instant, all of the mass is just moving in a straight line. And that line is continuously changing directions, but it is still ultimately just moving in a straight line. And we can figure out the kinetic energy and treat it as purely translational, purely linear kinetic energy, because the entire object is just following a single line. And this is the way that we would have done this in the past. And this should still work. And in that case, you don't need any rotational kinetic energy because you're just treating it as a single object that is moving in a line. You can also treat it as a single object that is rotating, though, with some sort of angular speed. And if you have an angular speed that you're using to describe how it's moving, then you don't need to have any sort of like linear interpretation of it. You can think of it as just a rotating object that you can describe with some angular speed, omega. Which means that we can interpret this object as having purely translational, purely linear kinetic energy, or we can interpret it as having purely rotational kinetic energy. Interpreted as rotational or translational linear kinetic energy. It doesn't matter which interpretation we use. They're both going to explain the motion of the object. If you are thinking of it as a translational, as a linear motion, you give a certain number of joules to the object to make it follow this linear path. And that number of joules is sufficient to explain why it moves in a line, and the line just happens to be in a circle. Or if you want to think of it as a rotating system, you give a certain amount of energy to make it rotate, and that rotation fully explains what's going on. And so unlike the rolling wheel, we can treat this as being pure rotational or pure translational, pure linear kinetic energy. So we got the same number of joules for both interpretations. So let's think about how we can use that then to come up with an equation for our rotational kinetic energy. So we know that our translational or our linear kinetic energy is equal to 1/2 mv squared. But we also know that if we want to interpret this as a rotating system, that the speed, the linear speed, is tangent to the circle, and that tangential speed is equal to r times omega. We also know that if we want to interpret this as a rotating system, where we'd be using omega, then we would be treating it as having rotational kinetic energy. But it would have the same amount of rotational kinetic energy because it takes the same number of joules to get it to move the way it's moving, no matter how we think about it. So if we want to think of it as a rotating system, the amount of rotational kinetic energy would have to be the same as what we get from 1/2 mv squared. So if we substitute both of these in, what we get is that the rotational kinetic energy is equal to 1/2 times m times r omega squared. And then I'm just going to multiply this out. So the rotational kinetic energy is equal to 1/2 m r squared omega squared. Now, we know that our rotational and our linear equations follow the same form. So we notice with linear stuff, kinetic energy is 1/2 mv squared. And here, we just have the rotational version of kinetic energy. And the linear version of kinetic energy is 1/2 mv squared, and so not surprisingly, our rotational version of kinetic energy has a 1/2, just like the linear one, and it has the rotational instead of the linear or the translational version of speed. So this is the angular version of speed squared. And so since we know that our rotational equations always follow the same form as our linear ones, we just substitute out the symbols to be the rotational symbols instead of the linear symbols. That must mean that if linear kinetic energy is 1/2 mv squared, and rotational kinetic energy is 1/2 times whatever this is, times angular speed squared, then this quantity, this mr squared, that must be the rotational version of mass, because we know that the equations always follow the same form. And so we just need to figure out, well, what does that mean when we talk about the rotational version of mass? What does it mean for what would be different about mass, or what is mass doing in a linear sense that needs a rotational version? And we know this is true because our angular and our rotational and linear equations follow the same form. So let's think about what mass is in a linear sense so we can understand what the rotational version of mass is. When we think about in a linear sense, mass is ultimately the thing that is tied to the concept of inertia. The more mass something has, the more resistance it has to linear acceleration. And we see that in F equals ma. It takes more force to accelerate a larger mass the same amount. So mass, what it's actually physically describing, in addition to how much stuff is inside of an object, is how much resistance a given object has to linear acceleration. And so the angular version of mass is going to do the same thing, or the rotational version of mass is going to do the same thing, except it's going to describe the resistance to rotational or angular acceleration. And so we have a different name for it, but it is just, in fact, the rotational or the angular version of mass. We call that moment of inertia. Which is the same thing as rotational mass. Moment of inertia is the far more common way you will see it described, but rotational mass is still an accurate description conceptually of what it is. The symbol for this is a capital I. So this is the angular or rotational version of mass. Just like regular mass describes the object's resistance to linear acceleration, this describes how difficult it would be to give a certain object an angular acceleration, to make it start rotating at a different speed. And we've already seen one of the equations for this. It turns out it's a little messier. The equation for moment of inertia depends on the geometry of the object and how it's rotating. But if we are dealing with a simple point mass rotating at radius r around some center, the moment of inertia for our point mass has got to be this term right here, this mr squared. The moment of inertia for a point mass is just going to be equal to mr squared. Where, of course, m is the mass, and r is the radius from the axis of rotation. This means if you take the same mass and try to rotate it around a circle with a larger radius, it will be more difficult to rotate. And you can feel that if you have a moderately heavy object and you just hold it like against your body and try to spin, it'll be relatively easy to rotate your body. But if you then try to hold it at arm's length, so the same mass but at a much larger radius, you will notice it is much more difficult for you to spin around. It's going to provide more resistance to that angular, that rotational acceleration. And just like you can sum up the mass of the parts to figure out the mass of a system, if we have a more complex shaped object, which we can treat as just a system made up of a whole bunch of points, you need to sum up all of the individual moments of inertia, just like you would sum up all the individual masses to figure out the total mass. So for a complex shape or system, The moment of inertia for the total shape or the total system is just going to be the sum of the moment of inertia of all of the parts. So you just figure out how many parts you have, figure out what each of their individual moments of inertia are, and then you add them all up, and you get the total moment of inertia for the entire thing. And the unit for this is a little weird, but you can see it's got to be the mass unit times the radius unit, so it's just going to be kilogram meters squared.